And so we have, if you look at the slides for, again, we're in week 6 is where we're going to start. We have some diagnostics that we're going to go through. Probably take up to the break, maybe a little bit longer. And then there's some regression bonus topics, right? What more could you ask for? And so we have, we can talk about hierarchical regression, talk about nonlinear regression. We'll talk about variable selection methods that tend not to get used in the social sciences much anymore anyway. But we'll talk a little bit about a little bit about those 3 topics, and we might have to sort of look at our time to see how much time we have, and we'll determine which of those 3 topics might be most interesting to us, and we'll start with that one, and then we'll just get as far as we get. Because starting next Monday or next Wednesday, sorry, we're going to start talking about exploratory factor analysis, and because we got to get that done, because after next week it's spring break week, right? And then that assignment will be due the week after spring break week. And so we're going to be done with regression today, whether we get through all of the bonus regression material or not. And you'll have that material to look through. I won't, for the most part, that material won't be, especially if we don't talk about it in class, it won't be on an exam. And so, but if you do have questions about it, I'll be happy to, I will be happy to try and answer those either outside of class or during class. So let me get to our week 6. Did the video start? Did you see the little countdown thing? And so we want to think about how do we look at our regression analysis and be certain or have some confidence in the analysis that we did, so that we can publish it in a place and feel good about our results, in that they're somehow not just idiosyncratic to a set of data that you have that might have some oddities in the data. And so the approach that we'll take is to look at the tools that we started talking, or we talked about several weeks back, week 3, I guess, where we assess our data for missingness, we assess it for univariate and multivariate outliers, and we assess our data for normality. And so that should be the place where we start, and that should be the place that we start. And if we do that, that should take care of a lot of our problems. If you don't do that, you can expect that if you have outliers, they're gonna come up as you continue to work with your data. The fact that there are outliers will sort of surface. If you have non-normal data, that potentially could be a problem that surfaces as well. And my approach has always been, even though I'm always really anxious, I collect some data, I'm always really anxious to get it analyzed, because I want to see, do I have something here that's publishable, or are the results just null? I have to sort of hold back from sort of doing the quick analysis and do some of this work first, because what I don't want to have happen, and I've learned this lesson the hard way by actually doing it, what I don't want to have to happen is to quickly test the hypotheses that I wanted to test, find out that they maybe are confirmed, then go back and look at the assumptions of the data, and then maybe have to remove some data or whatever, and then go back and the hypotheses are no longer confirmed. And so then it's a dilemma. Well, it's really not much of a dilemma. It's either you publish something that has data that is clearly flawed, and you have that attached to your name, and you get to live with that every time you look at that publication. Oh yeah, that's the one where I had the bad data that I published. And so you could do that, and you might get away with it, but it just, to me, would not be a practice that I would advocate for sure, and it's one that will, I think, will catch up with you sooner or later. So, and then the other side of that is, if I do the analysis, and let's say I can't wait, I do the analysis right away, test my hypotheses, and they don't work out, I could then go back, I could then go check, and that seems sort of, what's the word that we use, sketchy or shady, or it doesn't seem like the way you do science, right? It's not the way that I was taught to do science. Test your hypotheses. If they don't work out, then go see if you can cook the data in some way to get them to work out better. And it's just, so the best thing to do is to take the time, and sometimes it might be, of all of the time that you spend on your analyses, you might spend 3/4 of the time looking for missing data and determining whether it's systematic or randomly missing, looking at outliers and looking at normality and making those fixes. That might take you, let's say you invest 10 hours in an analysis project, it might take you 7 hours just to do this, but it's time well spent. And there's no, you just need to do it up front. And one thing, and I think I've mentioned this in the past, normality would be a good example. If you have non-normal data, all things being equal, if you can somehow normalize that data with one of the transformations that we talked about, you are more likely going to get significant results. It doesn't, it only helps. It only helps in decreasing standard errors and increasing coefficients, be it correlation coefficients or regression coefficients, or even if you're doing t-tests. And so it's just really worth the time to do this work early on, like we talked about. And so hopefully that's a takeaway that you get from this class, that you should this is the best practice. And then after we do that and we run our regression analysis, there's some diagnostics that we can check that's related more specifically to the regression analysis. And we're going to look at the degree to which the independent variables are correlated, which we call collinearity or multicollinearity. We're going to look to see if we have outliers in terms of outliers in terms of residuals. And so in some cases we might not have outliers when we check here, but they may show up as an outlier, or we may catch them in the first in our first analysis, where we're the first of the two-pronged approach. We might catch those outliers, and we may not then have them show up when we do the analysis with our regression specifically. And then we also are going to look for influential cases, which would be if your unit of analysis is individual, so each row of data is an individual. Some individuals might have a greater influence on your results than others, and so we want to assess that and make some determinations about are there problems? If there are problems, should we try to correct those? And we'll talk through some logic about how we might go about doing that. So we're going to spend our time today, at least in the first part of class, talking about collinearity and outliers and influential cases. And so, yeah.
Just a question, Dr. Vincent, is like when we do the first approach and we get outliers, that even Tabashnik and Fidel and you said, like, sometimes we may keep them and proceed. In this scenario, when we do a regression and I keep it and proceed, do I consider, because if I proceeded, I no longer am considering the outlier, how does that impact?
So you do the
'Cause I had-
first of the two-prong, you check your data for outliers.
And I had 2 outliers when I did the multivariate approach,
Yeah.
and I just kept it.
You kept them in the analysis.
Yeah, and I didn't do this twice because
Right.
it said that I could have, it was at plus minus 3 stage deviation, I could have 1 or 2.
Yeah.
So,
And so you'll get another view on those to see are they potentially outliers in terms of residual, or are they outliers in terms of influential cases?
but,
And then you can make another judgment about whether you want to keep those or not.
so it doesn't matter if I'm running a regression or doing anything else. When I first find it as an outlier, if I think I can keep it, I can just continue on and then examine.
Sure, and then you might get another view into it, and you'll get another chance to decide whether you want to keep those cases or not when you do the. And the bottom line, and I know this is in one of the slides upcoming, and your textbook says this as well. The logic that makes the most sense to me is to ask yourself the question: if somebody else were to replicate this study, would they find similar cases? And if you answer that in the affirmative, yeah, they probably would, then you ought to keep them. But if you can't answer that in the affirmative, then you probably should remove those individuals. If that's what your unit of analysis is, you probably should remove those individuals from your data set. And so, that's all going to be context specific, right? All your data and what you're measuring, and it would be impossible to give more specific rules than that, but it's just sort of a general set of just logic to use to help you make that decision. And so let's say I did a study with undergraduates, and I had and they were undergraduates, and I had 4 people in my data set that were 65 or older. So you could ask yourself the question, if somebody replicated this study here at the University of Oklahoma, are they likely to have 4 people in their data that's 65 or older? Studying, I don't know that I've ever had a class with a 65-year-old in it. An undergraduate class for sure. And so, I did last summer. I bet he was probably 65. But he was actually a senior citizen. They can take classes here free. And so he was taking a free class, and I was teaching him statistics, and so I did. But that was just one. But that kind of logic, that kind of thinking about your data is what you need to be doing. And clearly, if you don't think others would find it, then you ought to remove them from your data set. If you think others would find it, then it makes sense to keep it in your data set, and then live with the results, whatever those results might be. So multicollinearity, or just collinearity for short, I think multicollinearity would represent, collinearity would just be 2 variables. And multicollinearity could be a situation where one variable is correlated with 2 other variables in your data set. And so, but the people use the terms interchangeably. And if you say multicollinearity, nobody's going to say, well, you must be talking about more than 2 variables. Or if you use the word collinearity, they're not going to say, unless nobody that I work with anywhere, or I've worked with, would say, well, then you must just be talking about 2 variables. And so multicollinearity and singularity relate to the adverse effects of highly correlated independent variables. And here I say greater than absolute 0.7. I don't know if that's the number I gave you earlier in the semester or like a couple weeks ago. So just a lucky guess on my part that number matches this number, because it really is, it's just 0.7 is just, if it's greater than absolute 0.7, you definitely need to look at it. But I would say if it's greater than 0.5, you probably definitely need to look at it as well. And so I just 0.7 is really just as much an example or as an illustration as it is anything. And then singularity, as we've talked about before, is that your variables are redundant. In other words, one variable is a combination. One variable is a combination of two or more other variables. And so it's the idea, let's say we have Democrat, Republican, and Independent, and we dummy code 3 variables. We dummy code one, if Democrat, 1, else 0. We dummy code another one, if Republican, 1, else 0. And we dummy code a third, if Independent, 1, else 0, right? And we know that any two of those is going to tell us what the third one is, right? If it's 0 on any two of those, it's going to be equal to the third one. And so that's what singularity is. They're perfectly correlated, as I mentioned in the class before. SPSS, it's like trying to divide by 0. It can't do it. It just can't invert. Has to invert a matrix, and it can't do that when things are perfectly correlated. And so other software will just give you an error message. SPSS just gets rid of one of the offending variables. I don't know how it picks the one, but like in the Democrat, Republican, Independent, it probably just picks the one that was entered first in the variable selection, and I think that's the one that it takes out. It makes some determination about, well, which variables are the offending, and then which of those 3 are highest in the order, I think, but I'm not sure. But what it will do for sure is it'll take out, if you have a situation where you have singularity, the analysis will run, but you'll get I think it's a warning. It really should be an error, but it gives you a warning message saying that it took one of your variables out. To me, it really should be an error saying that you made an error in the selection of the variables that you put into the analysis. You can't do that. You can't expect the algorithm to be able to make sense of that. And so collinearity causes both some logical concerns and the statistical problems. And so we'll spend most of our time talking about the statistical problems and how to identify those. But just logically, I don't know. It just shouldn't seem like a good idea. I don't think. It's just not a good idea to. Why would you include nearly redundant variables in the same multiple regression analysis? It just doesn't seem intuitively. It just doesn't make sense. So these two things are correlated 0.75. You might call them two different names, but the correlation is 0.75 or 0.85. Even though you're calling them different names, they're really not. The correlation is so substantial between the two that it logically sort of it just doesn't make sense. And so that's sort of the logical part. That why would you include nearly redundant measures, even if you call those measures different things? The fact that you call them different things doesn't matter. If the correlation is high enough, then again, they essentially are measuring the same thing. And so that's the logical part. The statistical part is that it inflates the standard error of B. And so what would that do? If we inflate our standard errors, think about, what do we use the standard error for? You just got done with this.
B divided by standard error equals T.
Yeah, and so if we inflate the standard error,
And it changes the signal.
yeah, it's going to make the ratio is going to be smaller, right? And so,
No meaningful difference between
what's that?
no meaningful difference between
Yeah, you're less likely to get meaningful results because the standard error is so high in comparison to the B. But it also, and I don't note it here. We'll see it in a little while. It also does strange things with beta. And what's beta again? Yeah, and so if we have highly correlated independent variables, your betas will be outside of the -1, +1 range. which should always be a red sign, a red flag that there's some problems with your data. If you look at the betas and you have a beta that's equal to 2.5 or 1.7, it should be a red flag that there's something going on. And we'll see here in a minute. And it's going to be highly correlated independent variables, and you'll see here in a minute how you can quickly identify that. So there's no agreed on criteria for a correlation that is too high. I give 0.7 as probably a good example or a benchmark or guideline that you might use. But for sure, perfectly correlated variables will preclude the calculation. So R is equal to absolute 0.1 is too high. Other extreme correlations, pretty close to 1, will also preclude calculation solutions. So there's some preferences that we can change in the regression procedure that will allow us to have independent variables that are more highly correlated. But this is the max that you could have in terms of even setting that preference, and we'll talk about that in a minute. And so,
Can I ask a quick question?
Yeah,
It might
good.
be on the slide. So, whenever we were looking at one of those charts, but the one with the Pearson, that's
Yeah.
where we first checked for collinearity, right?
yeah,
And then down there, like a couple of tables down, it produced another collinearity chart, but the
Yeah.
numbers seem kind of. So, what's the difference between those two?
yeah, and so the correlations would just be sort of a first check, and you could look at the correlations, and if you see that you have two independent variables correlated at 0.95, whoops, I did something wrong. And that would be, you could just take one of those variables out and then rerun the analysis. And so, and that would sort of be the preliminary sort of look at the data that you could take. And then the more concrete is what we're going to talk about now, which would be that table that you saw. Because remember, I told you to check a box.
Yeah.
Under statistics for collinearity diagnostics, and then add 2 columns to your beta table or the B table. One called variance inflation factor, one called tolerance, and we'll talk about those. All of those are used to assess collinearity. But again, the correlation would just be a first quick glance at it. And let's say we saw a correlation that was, if I saw a correlation that was 0.7 in that correlation matrix that prints towards the top, I might not get rid of that variable if I really thought theoretically it needed to be there. I might not get rid of it without carefully looking at tolerance, for example, to see if it actually is causing problems with the estimation or not, and then make a final decision at that point. Does that make sense?
Yeah.
If we have just an independent variable and a dependent variable, and I look at the model summary table, which has the R, which is the first table, but what if I have multiple IBs and DBs? Do I still follow the same kind of thought process? I just look at it, I look at the R value, and then I go ahead and look at the bigger table. Since I have multiple IBs.
So you have, and so I'm not quite.
How do I view the R statistic? If I have one IB and DB, then I actually know that the R reflects the relationship between them.
Yeah, and
multiple predictors.
And so remember that multicollinearity is only the correlation between the predictors. So when we only have one independent variable, there's no problem with multicollinearity. There can't be by definition.
So even that R, which comes at the very top, should be less than 0.7.
Which one?
The one that comes alongside the R squared and the adjusted R squared.
No, we're not talking about that one.
Oh, okay.
Because that's the correlation between, that's concerning the dependent variable and the independent variable or variables. The multicollinearity only relates to independent variables being highly correlated. Does that make sense? And so what we're going to do first, and this, I don't know. I think the sort of go-to measure for me is tolerance, to assess. It's just because I understand it, and it also prints off first after when you get the table with the B's in it. It's in that table, and so I always look at that before I look at the other collinearity diagnostics that SPSS prints out below. And so we'll start here, and you can have a preference as you continue to work with data. But variance inflation factor or tolerance, and if you read the literature, but it's used widely, and people know what it is, and it's quite common. So we will examine tolerance, and then 1 divided by tolerance is equal to variance inflation factor, and so you can just remember that. We'll talk about how do we calculate tolerance, and then 1 divided by tolerance, or the inverse, is equal to variance inflation factor. And I say that these are the most common collinearity diagnostics, and that's just anecdotal on my part. I don't have data to support that. But tolerance, so this is the key paragraph right here, or the 2 key points right here. Tolerance for a given independent variable is computed with multiple regression by making that independent variable the dependent variable and keeping the remaining independent variables as independent variables. And so we don't have to do this manually. When we check the box collinearity diagnostics, it runs all of these for us for all of our independent variables. But we could easily calculate them by running multiple regressions to get each of the tolerance statistics, because it really is just that. If I want to get the tolerance for a given independent variable, I make that variable the dependent variable in an analysis, and then all of the other independent variables stay as independent variables. The dependent variables goes away, right? Because remember, collinearity is only between the independent variables, right? And so let's think about this. For a minute. Well, let's just finish this. What we do then is we get the R square for this equation that we ran, and the R square for this equation subtracted from 1 is the actual tolerance value. And so we take the R square, 1 minus R square is tolerance. So let's think about if we, and let me see if I just like being concrete. So this is the same data that we worked with last week, and if you have the notes, you'll be able to read it a little bit better than you can read it here. But I'll sort of work through this. Let's say we want to calculate the tolerance for. Remember, our dependent variable is how frequently they attended religious service, right? Yeah. And one of our independent variables was how often the participant reports that they pray. So that was one of our independent variables. And so let's say we want to calculate the tolerance for how often they pray. To do that, we take the dependent variable out of the analysis. We move this variable from an independent variable and make it the dependent variable. We click run. We look at the R square. 1 minus R square is going to be equal to our tolerance. What does R square? What does R square? What does that tell us? Not this specific R square, but more generally, What is R squared? What is R squared? It's a measure of effect size, right? Higher R squares mean what? Thank you, right. So it means another way to interpret that is a higher correlation between the independent variables and the dependent variable, right? And because that's the way we're making the explanation that there's a strong relationship or stronger relationships between the independent variables as a group and the dependent variable. And so if we find a really large R square, when we put how often they pray as the dependent variable, leave all of the other independent variables as independent variables, what does that tell us? And the R square is really high, let's say. What does that tell us? What's that? It should be reworked?
Removed.
Potentially, anybody else? What does that tell us? A high R square. Yeah, it's telling us that if we have a large R square with this recoded how often they pray as the dependent variable, that means the group of independent variables that are left in the analysis have a high correlation as a group anyway with this independent variable that was actually the dependent variable when we calculated tolerance, right? Does that make sense? And so intuitively, hopefully that makes some sense. And if we just sat around and if we had nothing better to do but think about ways that we can assess whether our independent variables are highly correlated with each other, I bet we would come up with something similar to this. Because it intuitively makes a lot of sense. Well, let's just make each of these independent variables a dependent variable. Keep the other independent variables as independent variables. See how high the R square is. If the R square is really high, well, that suggests that those independent variables are strongly correlated as a group or individually with the independent variable that we're assessing, right? I bet we would come up with that if we had time to brainstorm and to think about that. And so the smaller the tolerance, the greater the level of collinearity. Because remember, we're doing 1 minus R squared. So if our R squared is 0.9, 1 minus 0.9 is going to be 0.1, right? And so smaller values signify greater problems. By default, SPSS excludes independent variables with a tolerance less than or equal to 0.0001. So it's just some logic that's built into SPSS that if the tolerance level, which means the R squared between that independent variable and the rest of the independent variables was 0.9999, right? Very, very high, almost redundant. And so SPSS will remove variables or exclude independent variables if the tolerance level is less than or equal to 0.0001. You can adjust that, but you have to write some syntax. And if you did a Google search, you'd be able to find the exact line of syntax that you needed. But there's still limits on how low you can go. That's the 10 to the minus 8 is as low as you can adjust it in SPSS. Not a good idea. If you have to adjust it, if you have to make any adjustments, you really need to know. You really have to have a strong sense that this is the right thing to do, and to know what you're doing, because it really will cause a number of problems for you. So
Do we
Uh,
only adjust the ones which are less than 0.001, not the ones which is 0.1, even though it's a concern?
So for this particular point here, this is saying that by default, it's always at 0.0001 for all of your independent variables. If you want to make that lower, you don't set it lower on a per independent variable basis. You set it for that analysis. It's just a line of syntax that you add to the syntax for the. What's that?
Do you recommend changing that?
I don't recommend changing that. Unless you are really confident that you know what you're doing. There would be I was working on a project with Amy Johnson. Maybe I've done a couple of them over the years. And there's other ways, if you have highly correlated independent variables, there's other statistics that you can use that make an adjustment for that make a better adjustment than this sort of brute force method that we're talking about here. So I say tolerance values less than 0.1 should be a cause for concern. But you really need to determine for a given situation how to address the collinearity. Just because it's less than 0.1 doesn't mean absolutely it has to be deleted. But it should be a cause for concern. And again, it'll be up to your judgment and professional understanding of the data that you're working with to make that final decision. So in our case, tolerance for I think this is a measure of how well we understand tolerance. Tolerance for how often they pray looks to be 0.80. Did somebody have the slides? Is it 0.80? So it's 0.80. What was R squared? What was the R squared then when we did that? When this was the dependent variable? What was it?
0.2.
Yeah, it'd be 0.2, right? And so let's see if we can reproduce that. Let's just do a quick analysis using the same data and see if we can get this R squared that would be 0.2. Everybody understand why it's 0.2? Because it's 1 minus the R squared, and 1 minus 0.2 is 0.8, and that's where we get the 0.8. Does that make sense? And so if I wanted to, see, it looks fine on my screen. It just looks really fuzzy up there. Yeah. So if I wanted to bring up some data that so this is the same data that we used. Let's make sure that first I can reproduce the analysis. So that's my dependent variable. That looks to be the independent variables. I need to do statistics. I need to do descriptives and collinearity, right? Say OK. And we're going to skip to here. Yeah, so again, you can't see it very well. I wonder if I change the resolution. Well, you have to trust me. This is 0.8. This number right here is 0.8. So if I wanted to demonstrate that where that 0.8 comes from, what would I do? What's the first thing I need to do? So I'm going to go back to my linear regression analysis. I'm going to get rid of the dependent variable, right? Because remember, collinearity is only the independent variables. Then what am I going to do?
How much do they pray up to the dependent variable?
Good, thank you. And then I'm going to just run that. And what should the R squared be again? Should be 0.2, right? 0.2, you have to trust me. That's 0.2. I can change the resolution. It's really clear here. I can change the resolution on the break, and you'll be able to see the screen a little bit better. But it is 0.2. And so it's 1 minus 0.2, which gets us the 0.8 that we have on that gets us the 0.8 that we have. So that looks clear, doesn't it?
Yeah, it does.
So
It gets us this 0.8.
So R
Amanda.
plus tolerance should be 1.
The R squared that you get from doing that analysis plus the tolerance will always equal 1. Yeah, good point. So that's tolerance. And do we have any problems if we just look at our independent variables in this analysis? Do we have any problems? Right, I said a cause for concern would be 0.1, less than 0.1. What's the lowest we have? The 0.8. Yeah, and so smooth sailing, right? No problems. No problems at all. By the way, one of the things that I'm going to do it now, even though I'm a little bit late. So one of the things that I didn't go over the homework for next week, and I usually like to go over that so you have that in the back of your mind. So this is due not today, but next Wednesday, yes? And so you're going to use the same multiple regression analysis that you did for assignment 2, right? Assuming I don't send you any notes back saying that you need to change your analysis for assignment 3, right? Then you can use the same analysis. And you're going to use multiple methods to assess the multicollinearity. We just talked about one of them. That's tolerance and its inverse, variance inflation factor. But we'll talk about another one here in a minute. You're going to determine if you have outliers in your multiple regression analysis. You're going to assess the impact of individual cases to determine if you have cases that are having a disproportionate impact on the estimates. And by the estimates, I'm talking about the B's. And then be certain to fix, to the extent possible, problems identified in 1, 2, or 3. And if you do decide you're going to eliminate some variable or you might have to eliminate a variable because it's strongly correlated, and that might be the only solution is just to eliminate one of your variables because of multicollinearity. Of course, you'll have to rerun your analysis if you do that. Because the next thing that I need you to do is to interpret all of the relevant output and then write your results as if they were a part of a manuscript being sent to a conference or a journal and include a table. So that's sort of the common, that number 5 is something that you'll see it wasn't in last week's homework because it didn't make sense. We're going to do it with this week's homework, but you'll see it in every other homework that we do where I think there's some value in having you sort of distill all of that information down into a paragraph or in some cases maybe just a couple sentences. And then you're going to include your, of course, well-organized and neatly annotated underline neatly annotated SPSS output, okay? Questions on assignment number 3? Sorry I didn't go over that earlier. Most of you probably had seen it already. So that's what you're going to do for this week. So we've already talked a little bit about how to assess multicollinearity and you know what it is. You know how when you use PowerPoint, you have a presenter view on the screen? And I usually turn the presenter view off, so if you look at the video, you just see the same thing as this, as opposed to the presenter view where you just get a smaller slide. So if I turn the presenter view off, for whatever reason it gets really fuzzy. If I leave the presenter view on, it stay. I don't know why. I don't know why that would be the case, but it is. So I think what I'll do is, just because we have a couple of these smaller tables and so I'm going to leave. When you see the video, you're going to have to. It'll be in the presenter view. If you happen to go through it, it's not. It could be worse. Then at least we'll be able to read the numbers here. Okay.
Can I?
Yes.
I'm
Yes.
gonna ask this and see if it goes the right way. But you're really good at like rewording people's like. Okay. Anyway, so is there a reason that like the tolerance numbers for how often prey and strength of affiliation are like, is that the one that is probably highly correlated with, since those numbers are the closest together? Or does that not mean anything?
You wouldn't read that into this.
Okay.
There's the other analysis that's done at the bottom of your output. It will allow you to pinpoint the two independent variables that are most likely highly correlated. But let's say this was equal to 0.09. There would, in all likelihood, one of the, and not in all likelihood, for certain, one of the other independent variables is also going to have another low tolerance value. May not be exactly 0.09, but it's going to probably be really close to 0.1 or lower. But in this case, I don't think that I would necessarily, because these two are the lowest, that I would come to the conclusion that these are the two that are most highly correlated. They could be, and I have to think about that a little bit. And sure, we'll see. I do some examples here in a little bit where I intentionally have highly correlated independent variables, and we'll see that, and maybe it might help me think through it a little bit more. But you might be onto something, particularly when we get to the extremes, greater than or less than 0.1. So far so good. And then of course, variance inflation factor is just 1 divided by tolerance, right? 1 divided by 0.8 is going to be 1.1. 1 divided by 0.8 is going to be 1.251. If somebody wants to punch that into their calculator to confirm that, but that's what it would be. And so I don't know. Some people have a preference for, and I don't know why. Somebody came up with, well, here's this thing that's called tolerance. And then somebody else says, well, I want to use the inverse of tolerance. And we get both of them. And it's the inverse isn't particularly helpful. 1 divided by 0.1 is what? 10, right? 1 divided by 0.1 is 10. So if you decide you want to use variance inflation factor, you should be looking for values that are 10 or greater. But if you want to just stick with tolerance, that will be all you'll need to do for this class. But if somebody happens to give you a variance inflation factor, at least you would know what that is. Microsoft wants to update my office. So this is the second approach, and this is, if you scroll down your output, if you click the box for collinearity diagnostics, you'll see this printout as well. And this is a second approach to assessing collinearity. And when I tell you in the homework assignment that you should use 2 approaches, the expectation is you'd use tolerance and this approach. You can use them both. Don't use tolerance and its inverse variance inflation factor because they're just too similar. So the two approaches would be, this would be the second of the two approaches. And so it's fairly straightforward. We're not going to spend much time on how the values in this table are calculated. They're way beyond what I care to have us take away from this class. What we're going to do is just sort of focus on, or not just sort of, but we're going to focus on understanding what those values represent, or more specifically, how to interpret values that might be problematic. And so it's sort of a two-step process. We have this thing here that's called the condition index. We look for condition indexes that are greater than 30. In my case, I have no condition indexes that are greater than 30, so I'm done. Right? None of these. The highest one is 20.2. None even get close to 30. Stop. No need to go any further. But if you did have a condition index that was greater than 30 for one of the dimensions, you would look at the variance proportions, heading variance proportions, and we have 1, 2, 3, 4, 5, 6, 1 for each of our independent variables. You'd look at the variance proportions greater than 0.5 for at least two different variables, not including the constant. And in our case, we don't have anything that's greater than 0.3 or greater than 30, so we don't have to look at these variance proportions. But if we did, let's say that the last one was greater than 0.3 or greater than 30, sorry, we would not look at, it's not the constant, but it's looking at each of our independent variables, and we look across to see which 2 or 3 or 4 have a variance proportion greater than 0.5. What's that?
What if you don't have one?
Well, then you're good. So
Even
greater
if
than
it's
30, even if it's greater than 30.
Okay.
So if it's greater than 30 and no variance proportion, and you have to have two variance proportions greater than 0.5. It's at least two different variables greater than 0.5. And so first step, look at the condition index. If nothing's greater than 0.3, stop. I'm sorry, for some reason I got 0.3 in my brain. If nothing's greater than 30, if I say 0.3 again, we're going to take the rest of the day off. Nothing greater than 30, nothing greater than 30. Nothing greater than 30, you're done. If you have something that's greater than 30, then you're going to look at the variance proportions and look for at least two variance proportions that are greater than 0.5. And if you have two, those two would be the signal that these two independent variables are highly correlated. Or these two independent variables are correlated to an extent where they're causing problems with your estimates. And you might have 3, which would mean that maybe the 2 are correlated highly with the third in some way that would be similar to the Democrat, Republican, and Independent example. Not quite, but something similar to that, where maybe two variables together in combination might be highly correlated with some third variable. Question?
I know, excuse me, we have to first look at the conditioning
Yeah.
index, and I'm also parallelly looking at it, and I kind of have similar, I have nothing greater than 30, but I have a couple of values on the variance proportion that's greater than 0.5. What does that
Doesn't matter.
even mean? Oh, it doesn't.
It means that you don't have any significant concerns for for collinearity. Um, does that make sense? And so this method of assessing collinearity is somewhat idiosyncratic to SPSS. I've not seen it in other software that I've used. I've researched it some over the years. You can't find a lot in terms of how the variance proportions are calculated. I know what eigenvalues are. Eigenvalues are a measure of variance explained, and so it's we just have to sort of take it with we just have to have in this case some faith that it is doing what it says it's doing, and I think SPSS has a history that would we should be able to do that without understanding exactly how the variance proportions are calculated or understanding the logic behind what the condition index represents. We're just going to look for values that are greater than 30 and 2 or more variance proportions that are greater than 0.5. And if you find that to be the case here, if you go and look at your tolerance, in all likelihood you're gonna see that they were pretty close to 0.1, if not lower than 0.1. So it's not like this is going to show things that you wouldn't find by looking in at tolerance. What this might do, at least what this might do a little bit better, or in a clearer way, it'll help you see more clearly which two independent variables are correlated and that are causing the problem. I think it's pretty straightforward if you look at the variance proportions here and you identify the two independent variables that are greater than 0.5. You've identified where the problems are. And so we didn't have any problems in the data that we worked with, but just to sort of get some data that we can work with, I took same analysis, and I took their age, and I just took the square of age. And so, of course, the correlation between age and the square root of age is going to be it's going to be high. I don't know what it is off the top of my head, but if you just take the square root of something, it's going to be highly correlated with the original variable. And I did the same thing. With education. And so if we look at the tolerance, again, what should we be looking for in that column?
Less than 0.1.
Do we have values that are less than 0.1?
Yes.
Yeah, in this case, clearly those four variables that right? It's age, it's education, it's age square root, and education square root. And so if these weren't the square roots, if they were other variables in our analyses, it would be a clear sign that we probably need to take some action. Likewise, if we look at the other collinearity diagnostics, what's the first thing that we would do?
Condition index over 30.
Greater than 30, and we have two that are greater than 30. We start with the largest. Do we have two that are greater than 0.5?
Yes.
Yeah. Highest year in school completed, and the square of education, not surprising. And then if we look at the other one, the 55.087, also greater than 30, and the condition index for those two are also 0.9 each, right? So it's a clearly there. It identified our concerns, the variables that we should be concerned with, because I just know that the square root of age is going to be highly correlated with actual age, and the same with education. So the one thing I don't talk about here, and I might talk about it later on in the presentation, but let's just take a minute to, if we do find independent variables that are highly correlated, tolerance values less than 0.1, what should we do?
Assess which one explains more variance and get rid of the other because it's redundant.
Yeah, and why would you do the first part? Why would you?
I don't know, maybe one that predicts maybe some points more.
Yeah.
Maybe.
Yeah, I think, I sort of, I like the way that you're thinking.
Yes.
And you might sort of bring some theory into that too. Which one is theoretically more important? And then delete the other one would be, but so that would probably be the most common way to handle highly correlated independent variables. Again, they're nearly redundant. They're explaining nearly the same thing, and they're causing problems. Logically, we ought to just get rid of one of them. And then it's really up to you to determine, and then make an argument for why you get rid of the one that you get rid of. Tyler?
So, I guess the answer is going to be subjective, but if you have two variables that are highly correlated, one is more theoretically important or justifiable, and the other explains more variance, which of the two would you eliminate? Is it just contextual? This one's more critical theory?
I think if I'm using my hat that I wore when I was here and I was working as an academic publishing, I would keep the one that's theoretically more important, because that's the one that's going to allow you to make that. That's what journal editors and reviewers care about, is contribution to theory, right? And so that would probably be the default for me. But in my job that I have now, we could care less about theory. We could care less about theory. What we care about is being able to predict some outcome with data with a high degree of certainty or a moderate degree of certainty. And in that case, the theory variable, I could care less about it, and I'd probably keep the one that's more highly correlated. But I'd have to get rid of one of the two, because if I kept them both, it's actually going to make my predictions worse than if I kept just one of them, because it is causing problems with the estimations. And if we look at, well, this isn't really that bad, is it? The betas here really don't get, I mean, they're not out of the ordinary. They're within that -1 to 1 range. But in some cases, when we have highly correlated independent variables, it causes problems sort of across the board. So that's, in practice, that's the step that really matters the most. Is, okay, I've identified highly correlated independent variables. I need to do something, and then you need to make the decision about what that is. Just the identification is the easy part, and then what you do is, of course, the more important and the more difficult piece. But it's the necessary. It's a necessary step that has to be taken. So far so good.
Do we do both when we're dealing with our own data sets? Should we recommend doing both the tolerance and then also check the
The collinearity diagnostics?
Yeah.
Yeah.
The statistics in both?
Yeah, so I asked you in the homework assignment, I asked you to use 2 different methods and do both of those. Use the tolerance and these collinearity diagnostics. which I don't have a better name for other than collinearity diagnostics, okay?
But when we're dealing with our own data,
I'd probably use them both.
oh,
Yeah, and in most cases, they're going to be in concert, right? If you don't see any problems with variance inflation factor or tolerance, you're not going to see any problems here. And if you see problems with variance inflation factor or tolerance, you're going to, those same problems will surface here. And so it would be the rare sort of the rare case where they wouldn't be synced up. Okay. So far, so good. So that's collinearity. And so we want to look at outliers, and in this case, we're looking at outliers. We're identifying outliers by looking at the residuals. And somebody remind us, what are residuals again?
Amount of variance that is left unexplained by the model.
A residual, what's that? Yeah, and so it would be the actual value minus the predicted value would be the residual value. And I think Tyler, to your point, there might be some way to roll that up into unexplained variance as the residuals increase. But I think for our purposes here, just think of residual as the difference between the predicted and the actual. And so we want to look to see where those are extreme. Sort of like William's example, or William's question at the beginning of class. He calculated a bunch of residuals, and they seem to be large. And so that's what we want to do. The most efficient way to do that is not to look at the actual residuals. And by the way, we can tell SPSS to calculate the residuals for us. We don't have to calculate them all by hand, and I'll show you in a minute where you can tell SPSS to save the residuals. And we can standardize the residuals, and that's the more common way to look at them. What would be the benefit of standardizing the residual? When I say standardize, what does that mean?
We don't need to deal with the discrepancies of different measurements that are not comparable. If I use different scales, then I can't compare really results. If I standardize, then I can compare those results.
Right. So we're gonna calculate our residuals, and then we're gonna standardize them all. So mean will be what? With the standardized residual, the mean will be what? 0. Standard deviation will be 1. Thank you. And we could do that ourselves, right? We could tell SPSS to calculate the residuals for us, and then we talked under descriptives. We could say, okay, convert all of these to a z, or there's a box that we can check under save called z resid, and that's the standardized residual. And it's just an easy way, more efficient way, because if you looked at the actual residuals, you'd have to know what your standard deviation is, and then you'd have to do some calculation. And so if I had a standardized residual that was -3, what would that mean?
Below 3 standard deviations. Below 3, yes, below the mean 3 times, I don't know.
Yeah, it's 3 standard deviations below the mean, yeah. And if I have a residual that is a value of plus 3.25, you would interpret that as meaning what? What's that?
It's an outlier.
It's an outlier, yep. And it's 3.25 standard deviations above the mean, and it's in all likelihood, it would be an outlier, right? Because within 1 standard deviation is what percent in a normal curve? 68? 68? 95-ish? 99-ish, right? And then so that 3 standard deviations would be 99% of your scores should be within 3 standard deviations. So if you have a standardized residual that's 8, it should be like red flags, alarms going off, right? That this is a 105-year-old within a class of 19-year-olds, right? There's something that's making this so extreme. And so we're just going to be able to tell SPSS, calculate the standardized residuals for me, and then we'll be able to look at those in a fairly efficient way. There are other ways, and if you take a class, I don't know if there's Ed Psych used to have some regression classes, but if you take a class that's just regression, you'll look at other. There's several variations of the regular standardized residual that some people have a greater affinity for. One would be called the studentized residual, which makes some small correction. I forget off the top of my head what it is, but in everything that I've ever looked at, there's just not much difference between all of these other ways of looking at residuals and then the more straightforward, just standardized residuals. So this is where I always just focus, and I can learn as much as I need to learn. Amanda, did you have a question?
Yeah, I'm still a little bit unclear on the standardized part.
Sure. And so,
What it means to be standardized.
I'm sorry?
What exactly it means to be standardized?
Yeah, and so we can think about this starting with the first point. If we calculate all of our residuals, right? So you'll have to get the predicted value for everybody, get their actual value, take the difference, and those will be our residuals. And those numbers, those residuals can be standardized. In other words, and when we say standardized, we usually mean that we're going to make the mean 0 and the standard deviation 1. And the formula to do that, does anybody remember? What do you want to write the formula on the board? Anybody remember the formula? What is it?
The square root of the observation minus the mean square divided by.
It's simpler than that. It's
X minus X
bar, yeah.
divided by the standard deviation.
Yeah, and so if you think about this, and this is so it's each x minus x bar, which is the mean, divided by the standard deviation. And so if we think about that in the example, each xi would be for that person, for that row of data, what was the residual? We calculate the mean for all residuals, and then we calculate the standard deviation for all residuals, right? We could just use descriptive statistics, and we say, give me the mean for the residuals, give me the standard deviation for the residuals. And then it would be xi minus x bar divided by standard deviation. And when we do xi minus x bar, the mean all of a sudden becomes 0, right? Because if xi is equal to the mean, the numerator is going to be 0, right? And so this first part centers the data around 0, so 0 is going to be the mean, the numerator here. And then the dividing by the standard deviation, or the denominator, sets the standard deviation equal to 1. And we could spend an hour or so going through that formula and sort of deconstruct that a little bit more. But it really, for our purposes, what we're going to have SPSS do is apply that formula to our data, and then we'll be able to look at our residuals. And what we're going to do is we're going to look for, in absolute terms, large residuals, greater than, say, 3, and see if we have residuals greater than 3. And if we do, that should be a sign that we might have an outlier there. And then we have to make some judgments about what we're going to do with that outlier. It doesn't mean that we automatically get rid of the person if our unit of analysis is people, but we probably need to do something. If you have a residual that's 8, you need to get rid of that person. There's just almost no questions about it. That's just such an extreme outlier. It's just unbelievable that you'd have an outlier that would be that extreme, unless that's just so. I don't even know. A Z table wouldn't even go that low, but the likelihood of that happening is less than the likelihood of you winning the lottery tonight, right? It's a very, maybe similar to the likelihood that the Patriots were going to come back in the fourth quarter and win the Super Bowl. But 8 is just it really needs to be. It's too large. 4, I would be concerned about, and I probably would say, are you sure that looks pretty large? And then if it was 5, I'd like almost demand that you need to do something because there's some problems with your data. We were working with a data company that was doing work for us, and they had Z values that were like 10, and bunches of them. And there's something wrong with it was a calculation thing that they did. I don't know what they did wrong, but it just, and a bunch of us in the room are data people, right? And so we saw that and it was, red lights went off, and that just can't be. You guys need to fix that. Something went wrong with a calculation that you did. And so, and that would be the case here, or whenever you're looking at standardized scores, if you see those greater than 4, really should be, sirens, red lights, and probably some action needs to be taken. And so here I say greater than absolute 2. At least sort of start looking at them to see if there's some strangeness with the responses that you have with that data. 3 probably would be a number that would also work. And just because you have large residuals, it should just be an alert that you need to study them and not necessarily delete the individual from the analysis, but it just you need to use your informed judgment to determine what to do. And so it's not a black and white. If it's greater than 8, it needs to be removed from the analysis. But other than sort of those extremes, it really does take a lot of good thinking on your part. And so let's just go through this quickly, and then we'll take a break here. So in SPSS, this is the same box that we clicked earlier to get statistics. There's this thing called case-wise diagnostics. And you can either click that for all cases, and it's going to print out a table, one row for every person in your data set. Probably not what you want. But you can set this at some value. I set it at 2.5. Because if I set it at 2, it was going to be way too long. If I set it at 3, there would be nothing there because they're all none of them are greater than 3 in the data that I'm working with. So you can sort of play around with what value you should set this at. If you set it at 3 and you don't have any cases that have a residual greater than absolute 3, you might change it to 2.5. If you set it at 2.5 and you still don't have anything, you might set it at 2 just to see what are the most extreme cases that you have. And of course, the lower you set this, the least likely it is that you're going to have to make any adjustments to your data. And so what that does when we click case-wise diagnostics, set this at some standard deviation, it prints out a table that looks like this. And this table is the case number, actually the row number within SPSS. The row number within SPSS. And this is the standardized residual in the next column, so that's the Z residual. And so in absolute terms, our highest is the 2.911, right? And then the next one would be the 2.838. Is that it? The very bottom one? No, 6.5. Yeah. And so case 608 and 1895 are the two that I probably would look at. And then the rest of this is what their actual score was in the data. This is what the equation predicted for them. And this is the residual. Does that make sense? So this is a pretty easy way to look at this. The other way to look at this is we can click the save button and we can tell it to save the Z residual, and we'll do that here after a break. And we could look at all of them. Would just be another way to do it, but you're going to get the same. You get the same results as you get here. And so in our case, what I would do is I'd look at the 2 or 3 most extreme, and we'll start with I have case ID. I don't know what. So I have row number 1895, and I have row number 2662. I don't know why I didn't do 608, the 2.911, but I just copied and pasted some of the data from 2 of the other ones that we can look at. And so 1895 has, they attend church 0, so they never attend religious service. But their predicted value was high. 6 meaning, and this might be one of the cases that we looked at last week, this person, their predicted value was that they attend church several times a week potentially. And if we look at their data, we can see that the probably biggest driver for that is they say that they reported that they pray a lot. And prayer was a strong predictor of religious service attendance. And this person never attends religious service, but they pray a lot. And so that's a unique combination, right?
And then it's the opposite of the blind person. They attend, but they don't pray much.
Oh yeah, so this person is going to church several times a week, and they pray. I don't know. I think 0 is the never, and 1 is just almost never, or just whatever one greater than that would be. And so in that case, the residual is also in absolute terms high. And so I think the question that you have to answer is if others replicated our study, would they find similar outliers? And I think I know people that could fit into both of these, and probably could several people. And so I would say, yeah, that even though the residuals are large here in comparison to the rest of the data, I think if somebody else replicated this study, they would find similar individuals in their sample of data. And so I don't think it would be a good idea to delete these people from the data set. You might use similar logic with your data and come to a different conclusion, right? Well, this is just so extreme. People, these values just cannot go together. Somebody who says, this is an old example, but they say they watch TV 18 hours a day, and they also say that they work 14 hours a day. Maybe there's something going on there where their work involves watching TV or something, but it would be it'd be a sort of a unique situation that you could scratch your head and wonder if others replicating your study, if they would find such a person in their data. And then if you come to the judgment that, no, I don't think others would, or it's unlikely that they would, then you would, the course of action would be to remove that individual from your analysis. And of course, report that in the write-up that you do of your analysis, that this person or these people were removed from the analysis because of whatever the rationale was that you used. So questions about residuals and outliers? Questions? So what you'll do for the assignment is, you can do it one of two ways. I'll show you the other way when we get back, but this is the suggested way to do it. Just click case-wise diagnostics, try a couple numbers, and see what you get, and then you can make some determination in terms of what you need to do. Break? So about 15 minutes and we'll get started again.
Stop.
Thank you. Let me...
Is that what you got for Christmas?
That you want to see. So
I
I
think
don't
it's
want to
brown.
see anything less than
Or is it like red? It's really pretty. I was looking at like the page and I was like, that looks